Welcome to my channel, NVH, Noise, Vibration and Harshness. Today we are going to talk about frequency measuring and checking of accuracy of it. Sampling was done by simple frequency recorder. Post-processing data was done in OCTAVE or MATLAB because these two programs have very similar syntax. Performing Fourier Transformate and plotting it. And finally, checking the accuracy. To do so, I used simple acceleration recorder made from microcontroller, PY board, and cheap acceleration sensor. As a frequency sample, I used 100 Hz sound played from YouTube from my mobile. Just I put the sensor on the mobile and play the sound. Also, I wrote a short script in Python which takes readings from the accelerometer and writes it to a text file on SD card. Let's get started. As a first, we take our results file, which is 100 Hz test.txt, and in the first column we have a vector of time, which is expressed in microseconds. In second column we have acceleration in x, and the next column is in y direction, and the third column is z direction. The sensor was put on the mobile horizontally, and these values are almost value of g, the Earth acceleration. Let's go to our script in OCTAVE, which executes the task. First, we need to load signal library, and next we are loading our file with our readings. So let's execute these two lines. Okay, we can see that a variable appeared in this window, what means that the data was successfully read to the memory of the computer. Next, we put into two variables to value t. Just this, it takes first column. Also, you can see that two lines are commented. If we wanted to load x and y values as well, we don't need them because we will only treat z value. So these two lines are commented. So z is fourth column from variable signal. Next step is to normalize z value. To do so, we need to divide whole z vector by mean value of z. Means average value, what is approximately, the number is approximately 2100, which is more or less a value of g acceleration. So let's do it and plot our signal. Okay, this is our plot. As you can see, the plot doesn't start from the beginning of the graph, because microcontroller runs, and this value of time t is not exactly from zero moment. The microcontroller just counts microseconds from start when it's turned on, and sometimes last after it started reading. So what we can do to move the whole graph to the left. To do it, we just need to subtract just first value of t, first value, this first value of t from whole vector. Yes, so let's do it. Run selection. And now we can plot again. Yes, and we can see that it started and value, mean value is 1g, which more or less should be Earth acceleration. Okay, what we have to do as a next step is to resample the signal to desired frequency. I decided to set the frequency, the proper frequency, to 1 kilohertz. Why we have to do so? Because even when we watch the plot again, so let's run it again. If we go closer, somewhere here, for example, we can see that this accelerometer doesn't sample exactly in the same periods of time. So it works irregularly. Distance between two readings aren't the same. So it's bad thing. We cannot use it to Fourier Transformate. So we have to resample to some proper frequency. So the microcontroller samples approximately 800 hertz. So I decided to resample to higher frequency, which is 1 kilohertz. To do so, we do this part of code. Maybe it's good idea to sacrifice another video about resampling and why we have to do it. And so let's plot these two signals. It's the same signal, but in native sampling rate, which is irregular, and let's call it proper sampling rate. So the blue line is native, is the original signal. The orange one is after resampling. So we can see, for example, these 2 points have big gap, and after resampling we have nice and smooth um, piece of line which is divided in the same distance, equal gaps in time values. Okay, so let's do Fourier Transformate. This is absolute value of results of function FFT, and from variable ZZ, which is interpolated signal to new frequency, multiplied by 2 and divided by length, number of samples. Also, maybe it's a good idea to sacrifice a separated video. Also, we divide first value by 2, because how Fourier Transformate works. Next step is to create vector of time, vector of frequencies. This is x value on the graph. So let's do it. And finally plot our result. And as I expected, beautifully we have one very tall spike at 100 hertz frequency. All around we have some noise because the sensor isn't uh, it is very sensitive. But when we saw the first plot, uh, which is good to show this one, for example. Yes, we can see that it's very noisy. So also we can expect some spikes, some values on the Fourier Transformate, which shows us amplitudes for different frequencies. So as we expected, after feeding the sensor with frequency of 100 Hertz, we have a nice spike exactly at 100 Hertz. Let's see it closer. Let's have a look. It works very accurate. So that's all for today's video. Thank you for watching. Uh, I encourage you to leave some comments under the video um, and subscribe the channel.